So that's the first thing. The next thing is I would really like to talk to people today about dynamic programming. So we've been talking about, let's see, what is, so we've been talking about, let's say, paradigms for thinking about building algorithms. And in particular, we've been talking earlier this week about greedy algorithms. And so, yeah, we were talking earlier this week about greedy algorithms, and we're going to talk in the future about divide and conquer algorithms, although we've talked a little bit about that in the context of sorting. So today I wanted to introduce another paradigm, which is dynamic programming. And this also gets at a question from last time, which is like, what are problems, what are examples of problems where greedy algorithms don't work? So the idea in dynamic programming is to think about the solution to a problem as in terms of solutions to smaller versions of the problem. So in particular, the idea in dynamic programming, and this will be more clear once I give an example, is dynamic programming works when you can think about the best solution for a big problem is related to making the best choice among solutions to smaller problems. So this is like recursively, this is basically like for like solve of n, do solve, do solve like, you know, like I'm making this up, but like n-5 and solve n over 2 and solve like maybe like n-13 and then use the best one. Okay, so this is the structure of like what problems work with dynamic programming. So these are the type of problems that work with dynamic programming. And then once we get a couple of example problems, then I want to talk about like how you actually go and implement this, because so spoiler alert, recursion is natural, but not the fastest way to solve these problems. So I'll get into that later in the live session. Okay, so the like kind of the canonical dynamic programming problem is making change. So in the making change problem, I live in a country with coins of denomination like 1 cent, 5 cent, 10 cent, 25 cent, and 50 cent, and $1, 100. So if I have like dollar coins, 50-cent pieces, 25-cent pieces, dimes, nickels, and pennies, how do I go and make change? So, so the idea is to make change for 97 cents. I have a number of options. This is either like a 50-cent piece, it's either a 50-cent piece plus change for 47 cents, or it's like a quarter, 25 cent, a quarter, yeah, a quarter plus change for 97 minus 25, 97 minus 25 cents. This is probably like 72 cents. What's the dime plus change for 87 cents, or nickel plus change for 92 cents, or penny plus change for penny plus change for 96 cents. So for example, so if I want to make change with the fewest number of coins, I can calculate the number of coins needed. I can calculate the number of coins needed to make change for, let's see, 96, 92, 87, 72, and 47, and take the best one. Okay, so this is like this is the structure of a problem that lends itself well to dynamic programming. This is we saw very briefly in class that this structure can also be used for this problem structure can also be used for shortest path, typically all pairs. We talked briefly about all pairs shortest path, but I want to go from A to B using any vertices as, let's say, like A to Z, using any vertices as intermediate points. Okay, question? Yes. Okay. Aha, okay, good. So, yeah, so William, maybe I should, so I just want to get through the structure of shortest path problems, but William says like, hey, you can use dynamic programming for making change, but like, isn't there a super simple greedy algorithm? And the answer is like, let's talk. So first of all, I just wanted to talk through the shortest path example from the all pairs shortest path chapter of the book, which we did in class one day. And the idea was, again, you think about your problem. Idea is to think about your problem as multiple options that, let's see. So multiple options that involve solving smaller problems, or smaller versions of the problem. So the idea with shortest path is you're interested in going from A to Z using any vertices as intermediate points. But to do this, we're going to think about like, okay, or in general, go from A to Z using any of, say, like B through Y as intermediate. So to do this, I can say the best path from A to Z using B through Y as intermediate is either, right? Either it is go from A to Y. It's either go from A to Y using what's the one before Y is probably X, and then so this is a smaller problem. It's a smaller problem because I'm using fewer intermediate nodes. I'm considering fewer intermediate nodes, and then go from Y to Z using, again, fewer intermediate nodes. So either I go from A to Y and then from Y to Z, or I go from A to Z using. So if I can, right, so the idea here, let me just toss this onto the next page. So the key here, the key here is if I can solve the problem, using B to X as my intermediate, that helps me build a solution where I'm allowed to use B to Y, which is a bigger version of the problem. So I'm basically, what I'm doing here is I'm considering only subsets of my graph. I'm saying, like, okay, I'm going to restrict myself to only using a portion of the graph that doesn't involve Y. And then if I can solve the problem on the version of the problem that doesn't really involve Y, then I can go and build up a solution where I'm allowed to use Y as a middle point in my path. So again, this might be a little bit confusing, but if you read the all pairs shortest path problem in the book, I just wanted to connect that to what we're doing with dynamic programming. Is there any question about, so like the type of problems where dynamic programming works are problems where I can think of solving a big problem in terms of like generally a choice between multiple options that involve smaller problems. Okay. Yeah, so let's go back to making change. Let me go and back to making change. And so it turns out we live in a country with really boring coins. So in the United States, actually a greedy algorithm always choose the largest coin less than the amount, right. So in the United States, I can say if I want to go from change 97 cents, I can change 97 cents by going, okay, what is the largest denomination? Yeah, what is the largest denomination of coin? It's a 50-cent piece. So this is a 50-cent piece plus 47, which is why is it? Okay. Which is 50 plus 25 plus 25 is the biggest thing, less than 47. So this is bigger than a quarter. So I use a quarter and I get, I believe, 22 cents, which is, this is going to be 50 plus 25. So for 22, I can use a dime is the biggest coin I can use. So this is 50 plus 25 plus 10 plus 10 plus 2, which is, of course, 50 plus 25 plus 10 plus 10 plus 1 plus 1. Okay, so here I changed to 97 cents using 6 coins, and William is absolutely right that in the case of the United States coins, there's no way that I can do better than this greedy algorithm. Right, does this, so why would I want to go do something as crazy as dynamic programming? What if I live in a more interesting country? What if I have 1 cent coins, 1 cent coins, 7 cent coins, let's see, 11 cent coins, 15 cent coins, and 25 cent coins? Different set of coins. So now if I want to change 18 cents, the greedy algorithm would say, let's see, the greedy algorithm would say that 18 cents is just going to be 15 plus 3, which is 15 plus 1 plus 1 plus 1. So 3 pennies in a 15-cent piece, which is 4 coins for the greedy solution. But 18 cents could be just 7 plus an 11. 2 coins. So greedy doesn't work for any possible set of coins. So for some set of coins, for like boring coins like we have in the United States, you can just use the greedy algorithm and always grab the biggest coin available. But for the problem in general, where you have many potentially different types of coins, then in that situation, we need a more powerful algorithm. Does that answer your question, William? Yep, okay. So it's just a weird idiosyncrasy of the United States that the greedy algorithm works. Okay. How do we do dynamic programming? So let me just jump to, yeah, why don't I? Okay. So implementing this using recursion is slow, and I'm going to put a problem on the next homework assignment to try to drive this home. But the idea here is that you end up solving the same small problem over and over and over again. So, for example, if I want to change, let's say, let's say that I want to go and change the 6 cents. So this is, well, let's say, okay. So how to best change 6 cents, which is 1 penny plus 1 nickel. So you can end up solving this problem over and over and over again, because you can end up in a situation where, like, this could be like my change 6 could get called when I'm considering 11 cents 5 plus change 6. This is like, right, so 11 cents is like a nickel plus change 6, but similarly, like, 16 cents is a dime plus change 6. And let's see, the like 31 cents is a quarter plus change 6. So you end up, if I'm going and trying to go change a large amount of currency, if I'm trying to change like a buck 31, I can end up calling the change 6 function, call my make change for 6 cents, can get called over and over and over and over again. And I realize that, like, this is probably not super clear. Yeah, I think this is not super clear at the moment, and so I'm going to have you do a homework assignment that asks you to look at, like, how the recursive solution actually works. But at the moment, maybe you can take my word for it that, like, you're going to call your function on an input of 6 cents many, many times, because there's many possibilities that involve looking at changing 6. Yeah. So the recursive solution is slow. Fortunately, we can do better than the recursive solution. The way that we do better than the recursive solution is to do, let's see, is to start at the bottom and work up. So, so our idea is, basically the recursive solution is starting at the top and working down. And if we start at the top and work down, we can end up accidentally solving the same subproblems over and over and over again. So typically when you implement dynamic programming, you start at the bottom and build upwards. So let's see, right? So like change change 0. So basically create an array list, or a list, create an array, I don't know, whatever data structure you want. But you want to create an array that keeps track of the answer, the answers you've already computed. So array bracket 0 is going to be equal to my change function on input 0, which should be 0, right? It takes 0 coins to make, it takes 0 coins in order to make a change for 0 cents. Similarly, like array 1 is make change for 1, which is just 1. And array 2 is equal to like 1 plus change 0. 1 plus change 1 is 2. So this is all like not very interesting. It starts to get interesting at like, this is actually, yeah, it's like 1. If we look at, say, like array 28, so array 28, it's going to be the max of the min. Array 28 is going to be the minimum of like 1 plus array 27. That's the penny. The nickel is going to be 23. The dime is going to be 18. The dime, the quarter is going to be 3. Yes. And so these are all things that I can look up. It's going to be the best way to make change for 28 cents is going to be the minimum of these things, which are all things I can just look up because I've computed them before. Yeah. Questions on this? Does this approach of like starting at the bottom, working up, keeping track of your solutions?
Does it get slower the farther you go?
So yeah, this is like, so what's the, so how fast, slow is this? So, at each step, we need to look up, so how many coins do we have? Like, so the number of coins we have, so let's see, how fast or slow is this? So at each step, we need to go and look up in our array, num coins, number of entries. So this is like penny, nickel, dime, quarter, 50 cent, and then like a silver dollar coin. I want to say silver dollar, but I realized that I think the most recent coin that the most recent dollar coin was the Sacagawea coin, which was not silver. But when I was young, it was a silver dollar. So let's see. So the number of coins we have in our country determines how many things we're taking the minimum of, but each array lookup is constant time. And what that means is that we're just taking the minimum of num coins, number of things, number of things, each can be looked up in constant time. So basically our runtime is each step is just order of num coins. And so the like, to change n cents, e.g. 131 cents is going to be O of n times num coins. And you'll see on the homework that this is much faster than the like top-down recursive solution. And the key is that because we're remembering everything that we start at 0, we go 0, 1, 2, 3. So by the time we get to 28, these are all things we've already computed. So we can just go and look them up in constant time. And it's going to be then like just the number of coins times the how many times through our loop. Does that answer your question, Ellie? No.
I have another question.
Okay, great.
I can see how this is useful if we want to change a bunch of different values, like 131.
Yeah.
But if we're only doing it once, like if I only need to change something once, is it faster to do this where I have to go from the bottom up and figure out everything? Like,
so the yeah, so the so I mean the short answer is it depends, but like usually because the top down recursive approach is actually really slow. So in particular, the the top-down recursive approach is actually really slow, and I don't. Again, uh, I don't have the right. I don't have the right picture to. Huh. Uh, uh, so this is let's look at it this way. So I promise you on the homework that is coming out soon that I will go look into detail on like the can we do better? Okay, so the answer, I think one of the things that Ellie is getting at here, I believe, is don't we risk as we are building upwards, don't we risk computing a solution that we don't end up needing? So this is like that we don't end up needing. So do I really if I'm going to change like let's say 130 cents, do I really need to compute change of 19, right? Like do we run the risk that on the way up we are going and computing some things like change of 19, which given the input that we care about turns out not to be relevant. And so yes. So we could end up computing things that we don't need, especially if we're in a country that has like a weird set of coins. So we could end up computing things that we don't need. So slightly better approach. The slightly better approach for solving these type of problems is to start at the top and go down, but store everything you compute in an array. So let's see. So this is like the slightly better approach, and it's not a huge runtime advantage, but it's slightly better. Depends on exactly like how many coins you have and what their values are. Is to compute, say, to compute change of x. Let's like look up change of x minus 50 in the array. If array x minus 50 exists, use it. And then the same thing for like 10. Then I'll do a dot, dot, dot in a minute. So the reason the recursive approach is bad is that the recursive approach is bad because you might end up computing a value over and over and over and over and over again, which is slow. And so the idea here is otherwise compute change minus 50 and store it in array x minus 50. So every time you go to the trouble of computing a value, you then store it in the array so that in case you ever need it again, you would go and have it available at your fingertips. Does that make sense? So that this solves the problem of making sure that you don't compute anything that you don't need, but it also makes sure that you don't. So the two things that slow us down. One, computing the same value many times. This is really bad C homework. So when I say many times, I mean you can end up with the right input, you could end up computing change of 6 over and over and over and over and over and over again. So this is like really bad. It is less bad to compute a value that you don't end up needing. This is less bad, but we can solve both problems. By starting at the top and storing everything we compute in an array to avoid recomputing problems we've already solved. Okay, so I think I heard chat. So I'm not sure exactly what you mean by caching. Hunt.
In Python, I'm probably using the wrong term,
Okay.
but yeah, essentially under the hood, it'll store the answers to a function. So in the future, when you call it, it's O of 1.
Yeah, so this is, yeah, so I don't know exactly what the Python implementation of that is. Like if that is implemented correctly, like your interpreter, I think what you're saying is that if your interpreter is sufficiently smart, your interpreter might be able to do this, simulate this sort of thing under the hood without you actually having to write code. And the answer is like, yes, that can work very well if you have the right interpreter. I don't know exactly how Python implements that, unfortunately. I could look it up. I can try to look it up by next time. But yeah, excellent question. So anyway, this is, I think this is, it's a little bit confusing the first time you see it, but this isn't rocket science. It's not like, I think, conceptually super, super difficult once you've played around with it for a while. And in particular, the biggest thing that I want people to get out of this section of the course is to think about dynamic programming when you're looking at think about dynamic programming when you're looking at problems. So let's see, 125 here. So is there any other questions on this? I've got more examples that I want to do, and I'm going to give you a homework assignment that features some. The next homework is going to be like dynamic programming and divide and conquer. But I just want to make sure the high level approach of, right, like this is like dynamic programming in a nutshell is that to solve the problem for 28, I solve the problem for a bunch of smaller cases and take the best one. And so that idea of thinking about problems in terms of, is this a case where dynamic programming could be helpful? Okay. Yeah, so I'm going to try to, William asked an excellent question, which is, how do you know like what paradigm to use? How do you know like when to use greedy, when to use dynamic programming, when to use divide and conquer? And the short answer is like, all I can think of is experience and like seeing a bunch of examples and like trying to solve problems using different approaches. When you are presented with an unfamiliar problem, like I think the most helpful tool is analogy to examples that you've seen before, but that's like not foolproof, and realistically, you just need to be in the business of designing algorithms and solving these kind of problems for quite a while before you like, you know, the more you do this, the better your toolbox and your like algorithmic intuition becomes. So like, unfortunately in the first class, like this is in a first course in algorithms, it's like difficult to provide a really cut and dry method of like what tool works best when. Not the satisfying answer you hope for, but kind of the way it is.